There's a very simple step-by-step process that you can follow to solve separable differential equations. And there's a lot of initial value problems that fall into that category as well that you can use those exact same steps to solve. Once you get the hang of it, it's really not confusing, and it really doesn't have to be. In this video, I'm going to show you an example of applying those steps, which I've been talking about in a few of my videos recently, so that you can really get the hang of this process and apply it on your own. So, if getting rid of the confusion and frustration on these types of problems is something you're interested in, be sure to stick around to the end of the video, and without further ado, let's go ahead and jump right into the example. The first thing you want to think about is what form is this differential equation in? Is it already in separable differential equation form, or if not, can we get it into that form? Well, in this case, we actually do already have one of the separable differential equation forms, which is if we have some function of x divided by some function of y. Okay, so we've already got it in the right form that we want, which is great, because what this allows us to do is to move all of our y's over to the left, move all our x's over to the right by just multiplying both sides by dx, and then multiplying both sides by y, leaving us with the dx's canceling and the y's canceling over here, giving us y dy equals x dx. Great. So we've got our variables separated. That was pretty simple in this case. Of course, they won't always be that simple, but in this case, it wasn't too bad, I hope. Okay, so then once we've separated our x's and our y's, we can throw on an integral to both sides of our equation. Then we can just integrate the left side and the right side. Similar to the last example we did, y to the 1, or y is the same as y to the 1, which we can then just use the power rule to integrate. So we would keep our base y as y, add 1 to the power, so 1 plus 1 is 2, and then divide by our new power. And then we would add a plus c1, and then same thing over on the right. On the left side of our equation, we had a dy here, which means we could treat y as our variable and integrate as you would hope to be able to integrate, treating y as a variable instead of treating y as a function, like you kind of have to do with implicit differentiation problems. So it's a little bit different there. So just kind of keep that in mind as you're working with integration with different letters instead of differentiation. The dy or the dx basically indicates what letter you treat as your variable. So since we have a dx over here, on the right side of our equation, we're treating x as our variable. So again, x is the same as x to the 1. We leave our base x as x, add 1 to the power, then divide by our new power, and then add on some unknown constant, which we will call c2 in this case. Then, again, we can basically start by moving our unknown constants over to the same side of the equation. c2 minus c1, we will just call a new unknown constant c3, just to simplify things. Keep it so we only have one unknown constant to worry about later on. Everything else in our equation will remain the same. Okay. Then we can multiply both sides of our equation by 2. The 2's will cancel there, leaving us with y squared equals the 2 times this 2 here, or the 2 divided by this 2 here. When we distribute this into our parentheses here, this 2 is going to cancel with that one, leaving us with just x squared. And then we're going to have basically 2 times c3, which a constant 2 times a constant c3 is just going to create a new unknown constant, which we will call c4. And then we can just take the positive and negative square root of both sides of our equation. Keep in mind, whenever you're taking the square root like this to solve for a variable, you need to take the positive and negative square root. But that squared and square root will cancel, leaving us with y equals the positive and negative square root of x squared plus some unknown constant called c4. Okay, so now we need to deal with our initial condition. We're not done yet. If you are getting some value out of this so far, hit that like button down below and that subscribe and bell icon while you're down there too. We can keep crushing it all term long in calculus together. Okay, so our initial condition, let's deal with that. So first of all, this is the part of the problem that we were given that is our initial condition. It tells us that y of 0 is -3, okay? I'm just gonna write that down here. y of 0 is -3. What does that mean? Well, it means that when you plug 0 into our function y, we get out -3. So essentially, since we know that our function y here is a function of x, when we're plugging 0 into that, that means we're plugging 0 in for x. So basically, when x is 0, we know that our output, which is y, since y is our function, our output variable is y, our output is -3, so y is -3. When x is 0, y is -3. That's what this initial condition tells us. So what we can do is plug in these two things into this equation here and solve for C4. So when y is -3, x is 0. Okay, so then we've gotten this down to a position where we basically just have a plus C4, plus our unknown constant. So let me actually, real quick here before we carry on, just jot down what we had here was y equals plus or minus. So basically, this is a general solution to our differential equation, not accounting for our initial condition. Accounting for our initial condition should give us C4. So I'll just write this general solution off to the side, and then we can kind of proceed with solving for this. How do we get C4 all by itself? That's really what we're trying to do here. Well, to cancel out the squared, or the square root, we have to square both sides. So that's going to give us basically canceling out the square root. It also basically cancels out the positive or negative, because everything squared is going to be a positive number. So it doesn't really matter if this is negative or positive. The squared is going to cancel that out anyway. So we're going to get -3 squared is +9 equals 0 squared plus C4. Okay, 0 squared is 0. So this is just 9, not G. 9 equals C4. So C4 is 9. We can go back to our general solution of our differential equation and replace C4 with 9. So now this is going to be the particular solution to the initial value problem given here. dy dx equals x over y, where y of 0 is -3. Since you stuck around to the end of this video, I'm guessing you did find it helpful in solving this type of initial value problem. However, there are other categories that a separable differential equation or initial value problem can fall into. And if you haven't done any problems in that other category, it might be a bit of a curveball if you end up seeing it on an upcoming exam. So just go click on that video over there, and I'll show you an example of doing another type of separable differential equation example so that you can really get these steps down and ace that next test.